Today we're going to talk about some measures of central tendency. Hopefully these should be fairly easy. Hopefully you guys are going to know these backwards and forwards sort of before we even begin. But for those of you who don't, here we go. So, some simple definitions. Let's talk about the mean. What is the mean?
The average.
It's the average. It's what people mean most often when they say average. Can we give a better definition of the average? Because people also sometimes mean median or mode when they say average.
So because I think mean, mode, and
so an average is a measure of central tendency. And there are several. There's mean, median, the mode. There are also other types of measures of central tendency, like the geometric mean. We weren't talking about that.
okay then.
It's a sum.
Of all data
It's the sum of all the data
and divide by
The number.
dividing by the total number of data that we have. Okay, we're actually going to get to that definition in the next slide or so. Basically, the mean is a score that's at a balance point. If you think about a teeter-totter, if you have a heavy person and a light person, and you put them equally far away from the middle of the teeter-totter, what's going to happen? This is what happens when I try to do teeter-totter with my daughter. It's 3, right? So boom, she goes up. If I'm not careful, she goes, whoa. So what do I need to do if I want to teeter-totter with my daughter?
you come closer.
Yeah, I'm going to come closer, right? And when I am at the right distance, then things balance out. So the mean is going to be the score that's like the balance point. All of the other scores on average are going to be equally far from it. So we'll see more what this means in the next slide. The median, what's the median? All right, good. It's a good thing I'm talking about these then. So median sounds like middle.
Average.
It is an average, yes, that's right, which is why we don't want to use average in statistics. It's also an average, it's a different type of average. And it's the middle, it's the score that's in the middle. The mode, what's the mode? Most? The most repeating score, the most observed score. It's the thing that you see most often, the most common score. Okay. So, let's talk about how, whoa, I think this should be how to find the mean. Weird. This must be the slide, you noticed at the beginning it said like, there's been a problem, there are errors. So this must be a bad slide. So, how do we find the mean?
Yeah, you sum all the data you have and then you divide it by the number of the data you have.
That's exactly right. We sum up all of the data we have. If we want to represent this with symbols, we use this sum symbol. We sum up x. X is just a variable that takes on different values, right? So we're going to sum up all of the different values that we've observed, and then we're going to divide by n, the total number of observations that we have, right? So if we have something like a student score of 90 and a student score of 100, what's the mean? 95, that's right. Okay. Let's hope more of the PowerPoint isn't broken. Okay, so how do we find the median? We're going to sum up all the numbers.
No, we will divide.
We're going to divide the numbers by 2. Sum up all the numbers and divide by 2.
I think it depends.
The highest one with the lowest, and like put it both of them and then divide by 2.
So we take the highest score and the lowest score. We sum those and we divide by 2, and that will give us the median.
So plus 1.
Plus 1.
Actually, that depends. Sometimes we have one midpoint, sometimes we have two.
Sometimes we have one midpoint, sometimes we have 2 midpoints.
So, for example, if we have only one, midpoint, like you take them, then that is our middle. If we have 2, then we find the mean of the 2.
Okay, so how do you know what the midpoints are?
There's two ways.
This is actually a computer science problem.
There's 2 ways.
Yeah.
The way when you have like just say 10 numbers and the way when you have 9 numbers, it differs. So when you have 9 numbers, you add 1 and then you sum of the highest and the lowest.
Like,
We're gonna do some.
like for example, say, 5, 10, 15,
Okay.
20. Now here you don't, okay. Now these 4 numbers, you don't have that. You don't have a direct number. If you have 25, then 15 will be.
Right. But now we have 2 middle numbers,
Yeah,
so we have 10 and 15.
So you have to find the mean for these 2, so that you'll be able to find the.
Yeah. So if we have 5 values, we take the middle one. And I'm asking, how do you find the middle one?
Just count.
You just count. So we had a value of 7, we had a value of 23, we had a value of 13, we had a value of 12, and we had a value of 1. What's the middle one?
13.
13. Shoot. Let me make this 12, and let me make this one 13.
Actually, we have to make it in order.
We have to order them, right? We need to order them. We need to put them in order. This is where the computer science part comes in. Because they're really interested in sorting things. So all we do is put these in order. Okay, 1, 7, 12, 13, and 23. And that one's in the middle. Yeah, I guess I should have left that 13 and 12. Right. We need to put them in order, right? Okay, so we're going to arrange all the scores in ascending or descending order, and then we're going to find the middle score. So for an odd number of scores, like he was saying, it's just the one that's in the middle, right? But what if we didn't have an odd number of scores? Well, what do we do if we have an even number of scores? What did you say, Allah?
The 2 in the middle, we find the mean for them.
We take these 2, the 2 that are in the middle, and we calculate the mean for that. Yes. So what is it? 12 plus 7, well that's 19 divided by 2. That's 9.5, right? Yeah, right. All right, so when we have an odd number of scores, we just find the one in the middle after we arrange them. After, if we have an even number of scores, there's not going to be 1 in the middle, there will be 2 in the middle. So then we just take, not the average, we take the mean of the 2 middle scores. All right, how do we find the mode? It's the most common one, so how do we find it?
The one that repeats a lot.
The one that what?
That repeats a lot.
Yeah, but how do you find the one that repeats a lot? This is a really simple question. You know, sometimes the simplest question is the one that people can't get. They're like, how do you find one? Oh, jeez, that's hard. You count them, right? All right, so here we've got 7, 23, 12. Let's say 12 and 1. Well, how many 1s do we have?
1.
We've got 1, 1. How many 7s do we have? 23. 1, 7. We have 12, 12, and 23. So we've got 2 12s, right? 2 of them. The rest is just 1, 1, and 1. So we count up how many times we observe each of the values, and then the one that has the most wins, right?
What to do when there's too much
When there's too much what?
number?
When there is too much,
Too many.
when there are too many numbers, what do? You use R. A lot of this stuff is really, really simple. If you're only dealing with 10 numbers or 20 numbers, but when you start dealing with hundreds of numbers, or today we're actually going to work with 1,000,000 numbers. We're going to work with 1,000,000 numbers for a little while today. And with 1,000,000 numbers, you don't want to count these by hand. Use R. Oh, now what would happen if we had 2 1s? We have 2 modes, right? So we can count how many of each score that we have. This is a lot easier to do if you've already arranged them in order to find the median. And then, excuse me, the score with the highest count is the mode. If multiple scores have the same mode, if two scores do, you call it a bimodal distribution. There are two modes. If you have 3 or more scores that have the same counts, that's the highest count, you just call that multimodal. So you have 10 scores with the same, and it's just a multimodal. Most of the distributions we're going to be working with are going to be unimodal. Uni meaning 1. Okay, so an example. Let's get the ages of the members. So we had a value of 7, we had a value of 23, we had a value of 13, we had a value of 12, and we had a value of 1. What's the middle one?
13.
13. Shoot. Let me make this 12, and let me make this one 13.
But actually, we have to make it in order.
We have to order them, right? We need to order them. We need to put them in order. This is where the computer science part comes in, because they're really interested in sorting things. So all we do is put these in order. Okay, 1, 7, 12, 13, and 23. And that one's in the middle. Yeah, I guess I should have left that 13 and 12. Right. We need to put them in order, right? Okay, so we're going to arrange all the scores in ascending or descending order, and then we're going to find the middle score. So for an odd number of scores, like he was saying, it's just the one that's in the middle, right? But what if we didn't have an odd number of scores? Well, what do we do if we have an even number of scores? What did you say, Allah?
The two in the middle, we find the mean for them.
We take these two, the two that are in the middle, and we calculate the mean for that. Yes. So what is it? 12 plus 7, well that's 19 divided by 2. That's 9.5, right? Yeah, right. All right, so when we have an odd number of scores, we just find the one in the middle after we arrange them. If we have an even number of scores, there's not going to be 1 in the middle, there will be 2 in the middle. So then we just take, not the average, we take the mean of the 2 middle scores. All right, how do we find the mode? It's the most common one, so how do we find it?
The one that repeats a lot.
The one that what?
That repeats a lot.
Yeah, but how do you find the one that repeats a lot? This is a really simple question. You know, sometimes the simplest question is the one that people can't get. They're like, how do you find one? Jeez, that's hard. You count them, right? All right, so here we've got 7, 23, 12. Let's say 12 and 1. Well, how many 1s do we have?
1.
We've got 1, 1. How many 7s do we have? 23. 1, 7. We have 12, 12, and 23. So we've got 2 12s, right? 2 of them. The rest is just 1, 1, and 1. So we count up how many times we observe each of the values, and then the one that has the most wins, right?
What we're going to do when there's too much
When there's too much what?
number?
When there is too much,
And too many.
when there are too many numbers, what do? You use R. A lot of this stuff is really, really simple. If you're only dealing with 10 numbers or 20 numbers, when you start dealing with hundreds of numbers, or today we're actually going to work with 1,000,000 numbers. We're going to work with 1,000,000 numbers for a little while today. And with 1,000,000 numbers, you don't want to count these by hand. Use R. Oh, now what would happen if we had 2 1s? We have 2 modes, right? So we can count how many of each score that we have. This is a lot easier to do if you've already arranged them in order to find the median. And then, excuse me, the score with the highest count is the mode. If multiple scores have the same mode, if 2 scores do, you call it a bimodal distribution. There are 2 modes. If you have 3 or more scores that have the same counts, that's the highest count, you just call that multimodal. So you have 10 scores with the same, it's just a multimodal. Most of the distributions we're going to be working with are going to be unimodal. Uni meaning 1. Okay, so an example. Let's get the ages of the members of this class. Groovy? Is that right? Is that everyone? All right, so these are the ages of members in this class. I don't want to have to do all this adding up manually, so let me use my friendly statistical companion, R. What's the median? How do we do this? How do we figure out the median? We need to order the sequence, right? So what's the lowest value here? 19. Okay, how many 19s do we have? 1, 2, 3, 4, 5. Okay, so we have 19, 19, okay? Then we have 20s, right? How many 20s do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, someone please count with me so we don't have to count this. 1, 2, 3, 4, 5. You guys count all right. That's it, right? Okay. So, now we have all of these in order. Now we need to find the middle one, right? So we have 22, which means what? How many middle ones will there be? Will there be one thing in the middle, or will there be 2 things in the middle? There's going to be 2 things in the middle, right? So we can find the one in the middle. Well, at this point, I can stop because everything else remaining is 20. But if these were different, right, I could keep on going on. We must be off somewhere. We're off somewhere because there's only one middle one left. Okay, but we've got sort of the mechanic down, right? That's how we find the median. So all we need to do, let's get rid of these now. We have them in a nicer form. And go ahead. So the median was 20. What is the mode? 20. How did you know? Well, we only had 5 19s. We had 8 21s. The rest we had 1 of, and we had a whole bunch of 20s. We had plenty more than 8, right? So 20 is the most frequent observation that we had, so that's the mode. Okay, let's go back now to find the mean for this class. So how do we find the mean for this class? I guess on the slide that was broken was when I introduced this symbol. So there are 2 ways to depict the mean. The ways we're going to use to show means in this class are using the Greek letter mu, and also using an x with a bar over it, x bar. One of these is for populations. One of these is for samples. Typically, when we're talking about a population, you're going to see the Greek letters. So if you ever have a question about, is this a sample, parameter, is this a sample statistic or a population parameter? if you look at whether it's a Greek letter or an American letter, often with a funny hat over it or something, you'll have a good idea. So typically the population parameters are indicated with the Greek letters. All right, so I said, what's the population mean for this class? I said population mean for this class, like it's the population of everyone who is here today, right? This is the population of students who are here. This isn't a sample of the students. I'm not taking some of them. I'm looking at the whole group, right? So this is a population. So I'm going to use the population parameter for mean here. So how do we get the mean? We need to add all these things up, right? Now, if you thought that finding the median was a pain in the butt, doing the mean would be even more of a pain in the butt. So, R, thank you. We have that, I believe, already in. Yes, we do. Okay, let's find the mean. Mean ages. Whoa! Just gave me the mean. Let's make sure that this is right. So we said that the mean is the sum of all of the numbers divided by the total number of numbers that we had, right? So, okay. So the histogram that R made for us automatically look like this. Now it groups different ages of people together. So it goes from 18, 19 to 20, 21, 22, 23, 24, 25, and so on and so forth. So this bar actually includes all of the people that are, doesn't make sense. That are 19 or 20. So I guess R here is using the cutoff. It's throwing everything that is under the value into the bar. Now, what if we don't want to know how many people are between 19 and 20? Instead, we want to know how many people are 19. What we can do is we can tell R what limits we want it to use. So here, like, the limits are from 18 to 20, 20 to 22, and so on and so forth. But we don't want those. Let's use some different limits. So, I'm going to set the limits here with this command called breaks. It's not that important. You guys, I'm not going to have you making histograms, at least not that I'm aware of, with breaks. I'm just doing this to show you what the distributions look like as you change these parameters. Okay, so if we do this, I also plotted the mean, the median, and the mode. So it doesn't, right. Okay, so here's our new histogram of ages. So 19-year-olds are here. We have, it says 5 of them. 5, right? 20-year-olds are here. We have, it looks like 22 of them. I erased them, but we can count them up. It should be 22. Now, what I've done here with the different colors, the red indicates the mean. So remember the mean I said was 20.4, oh right, with me it was 20.8 something. So this is fairly close to where 21 would be, right, which would be the center of this bar. Now, here I've plotted the median and the mode. I was hoping they would be different so you could tell them apart, but they fall right on top of one another, so you only see the one line here. Basically, the median and the mode both fall right there. Now, the way that this is plotted, it suggests something weird. Now, the limits, think of where these edges are. If this is 20, what are the limits for this? Here we have 20, here we have 21, here we have 22. So what are the boundaries? What are we saying is in this bar? Some 19-year-olds are in this bar. Or at least they look like they're in that bar based on the limits.
It's about the month differences.
Right, so there are some people who are just 36, like they're just barely 36, like me. Does anyone have a birthday coming up very soon? Like within the next month? So how old are you right now? You're 19, but very soon you're going to be 20, right? So this, the way that this is drawn, it looks like we have 19 and a half to 20 and a half, right? So this suggests that he might actually be in this category. So we probably didn't draw it the way that we really meant to draw it. I mean, yes, knowing what we did, we know that this indicates how many 20-year-olds that we have. But if someone else were looking at this graph, they might think that it's anyone between the ages of 19 and a half and 20 and a half. Does that make sense? So let's make a better looking graph. Let's use more realistic breaks. All right, cool. So now 20 falls right there, right at the border, right? So this would be like 20 people that are 20 to 21 fall within this region. Did anyone who is like almost 21 say that they were 21 even though they're 20? Probably not, right? So probably everyone that's really close to 21 still said that they were 20, right? So this more accurately represents what we have. Did you have a question? No. No. All right, now there's one other thing. Let's go to the slides for a second. So we got our raw histogram, and we didn't like the limits that it gave us, because it grouped people together where we wanted to see the individual differences. So we created our own limits, and then we didn't like how our first set of our own limits looked, because it suggests that people that are like 18.7 years old would have been in the 19-year-old group. So we made a better histogram. Now our measurements vary in precision. How many, how tall are you? 163 centimeters, right? Now if we took a measuring tape, would she be exactly 163 centimeters? Probably not. Probably not, right? She's probably a little above or a little below, right? You could use millimeters, but even if you use the millimeters, it might be a little bit above or a little bit below, right? So lots of our measurements aren't 100% precise. In fact, none of our measurements are 100% precise, right? There's some error in our measurements. So what do people do oftentimes when they're measuring things? They often move around, right? Oh, well, you're much closer to 191 centimeters than you are to 190 centimeters, so we'll say 191. You guys do that in Turkey? Round up, if you're closer?
Yes.
Yeah, okay. I was going to say, I say I'm 6'3". I'm actually not 6'3", but I'm much closer to 6'3" than I am to 6'2". So I have error in this measurement, right? So we're going to set the limits when we do this where we're going to be rounding. And this is better, but the values on the x-axis aren't going to accurately reflect the content of the bars. So we had the graph, right? And the 20 was right on the edge. Right? We had the bar, and then there was the 20. The 20 wasn't in the middle. So how can we create better labels? Well, we can set the midpoints. The midpoints are going to be the mean of the apparent limits. So what are apparent limits? Well, the apparent limits are these things, are the edges of the lines, right? It looks like it's at 20 to 21. Those are our apparent limits, okay? So we have apparent limits of 20 to 21, or for our first data point, we have apparent limits of 19 to 20, right? So, the real limits for our example are not these. I made them a little bit below and a little bit above. I'm sorry, a little bit below and a little bit below the next number above to indicate where that rounding comes in, right? Now the midpoint is just the mean of the apparent limits. So what's the mean of this? 19.5. So jumping the gun, let's do this. It's so much better. This really is so much better. Because here we have 21.5, right? So 21.5 is like in the middle of the 21-year-olds, right? Some of you should be above 21.5, some of you should be below 21.5, some of you might be exactly 21.5, but this label now really accurately sort of describes what's the middle, what's the value that we're interested in, and then with the limits that we have a really good idea about what we're applying. So this is much, much better. All right. Imagine that we're measuring height to the nearest centimeter. Let's say we want to group people into bars with apparent limits similar to the following: 120 to 130, 130 to 140, 140 to 150. So the question is, what are the real limits? Those are the apparent limits, right? Now I said we're measuring to the nearest centimeter, right? So what would the real limits for this be? 125? 135? 145? Who agrees? No one. You don't even agree with yourself. Who disagrees? No one. Okay, we need to discuss limits more. So, we have our limits, right? Those are the lines that we're plotting. Now, our measurements are inaccurate, right? And we do some rounding. So, at what point do we round and say, okay, 120, we're going to say 120.
Less than 5.
When it's less than 0.5 away, right? Or actually, the rounding rule that I use is 0.5, you round up.
Yep.
There are other people who say that this introduces bias, and it does. If you always round up, then you are introducing a little bias. But I'm okay with a little bit of bias because we're doing it the same way everywhere that we're doing, so we'll just forget about it. Forget about the bias. So we're going to round up at 119.5, right? So this looks like 130. What point do we round up and say 130?
129.5.
129.5. So these are the apparent limits. This is what the limits look like, right? We talk about people being 120 centimeters, 142 centimeters. We don't say 121.5, right? Some people might. That's not very clear, right? So the real limits are the things that we're basically describing. Okay, it's 120. It's 130. What's your IQ? It's 112. Okay, it's 112.12. No, 112. Right? So, these are the real limits for those apparent limits. What are the real limits for these apparent limits?
The same, like this is minus. Like
It's not the same,
okay.
but we're doing the same thing. Okay, so what is it?
129.5.
129.5 to 139.5, right? Okay, how about 140 to 150? 139.5 to 149.5, right? So those are our apparent limits. The real limits, we're basically just subtracting 0.5 from our apparent limits. Okay? All right. What are the midpoints?
25, 35.
Not 25, 35, and 45. 125, 135, and 145. Yeah, that's exactly right. See, Bob, this is what you were thinking about earlier. So the midpoints It's just the average of the apparent limits. Not the average of the real limits. It's the average of the apparent limits. All right, so we get 125, 135, and 145. Great. Imagine that your teacher is assigning some grades. Let's say that they're using the following real limits. So B naught minus is from 79.5 to 82.5. A B is 82.5 to 86.5, and a B plus is 86.5 to 89.5. Those are the real limits. What are the apparent limits?
80 to 83.
80 to 83. 83 to 87. 87 to 90. That's right. So we're just adding the 0.5 back to our real limits to get the apparent limits. What are the midpoints?
No.
No.
81.5.
81.5?
84.5.
No, actually not 84.5. 85. And 88.5. That's exactly right. Brilliant. Now, the histograms normally have equal ranges, equal lengths. So before, when we were doing it, we had 20 to 21, 21 to 22, 22 to 23. But notice here, this goes from 80 to 83, and then this goes from 83 to 87 instead of 83 to 86. So if you were creating a histogram from these data, if someone saw this, they would need to be careful, noting that this is actually bigger than the other ranges. Do you have a question?
Yeah. When we calculated the midpoints, we said we have to go to the real limit.
Yes, we are using the real limits. 81 plus 83 is 163 divided by 2 is 81.5. Right? 83 plus 87, let's forget about the 80s.
But these are the apparent limits.
These are the apparent limits. I'm not taking the midpoints from these. I'm taking the midpoints from these.
No, but 79.5 is the real limit.
87, what?
That's the real limit.
Which one? I'm sorry.
Okay, 79.5 to 82.5, that's the real limit.
The real limit.
So are we using that when we...
No, we are using the apparent limits. Did I have this wrong on the previous slide?
No, yeah, if you go back. So to calculate the midpoint, what do we use?
The midpoints, here we go. Midpoints are the means of the apparent limits.
The apparent limit.
So we are using the apparent limits, right? The apparent limits here, 19 to 20. The midpoint of the apparent limits is 19.5. The midpoint for the real limits, I think that would be 19.45, right? But we're not using the midpoints for the real limits, we're using it for the apparent limits. Let's go to the next slide to see if we were consistent. So the apparent limits, the midpoint should be 125. Well, that's what it was. We are using the apparent limits when calculating the midpoints. And again here, what are the midpoints? 81.5. That is calculated using this, not using this, or this would be 81.45, I think. Right? So we're going to use our apparent limits to calculate the midpoints. Okay, so be careful. If you get a histogram, make sure you look at the labels to make sure that each of those bars represents an equal amount of stuff. Okay, so what grade does a student get? So a student got the score of 87, and the apparent limits are 83 to 87 for a B, 87 to 90 for a B plus. What? They get a B plus. How do you know? I mean, that 87, right, that's this point here. So if you got exactly an 87, well that's like touching both of those bars. So how do you know that they get the B plus? Because of the real limits, yeah. A score on the border is going into the higher category, and this is obvious if you inspect the real limits. Right? The real limits say that it's 82.5 to 86.5, 86.5 to 89.5. Right? So, an 87, B plus. So, you guys can thank real limits for the way that I grade you. Because there are some teachers that will say like, oh, you got 86.999999999, B. I say, I use statistics all the time. I'm going to use real limits. B+. Okay. So we know how to create histograms. Let's create a whole bunch to understand what a probability density function is. Because probability density functions. Oof. If you know calculus, they're really easy. But without, man, thank goodness for R. So I'm going to sample from a distribution 1,000,000 times. So we talked about flipping a coin like 10 times or 100 times. I'm going to sample from a distribution 1,000,000 times. Oh, actually, I've already done this. I've already generated the graphs. You can look at the code on the internet if you want to see how I did this. Okay, so when I sample from 1,000,000 times, what's the law of large numbers telling us? It's telling us that the estimates that we get are going to be very similar to the true probabilities of things, to the true frequencies that you would observe, given the underlying distribution, right? Thank goodness for the law of large numbers. All right, so we have a histogram with 5 bars for some distribution. These frequencies, they're huge. 6e, the 5, so that's 6, 1, 2, 3, 4, 5. It's 600,000. So we are observing between 0 and 100, 600,000 times. We are observing between 100 and 200, about 300,000 times, right? This is giving us an idea about the shape of the distribution. If we wanted to guess what shape the distribution has, we might draw some line like that, right? Sort of going through and covering up that. Let's use more bars. Here's the same data with 10 bars. So instead of going from 0 to 100, I'm going from 0 to 50, and then 50 to 100, right? Now you notice, instead of it looking sort of like this, it actually kind of looks like this, right? Now, if we do this with 100 bars, we now get something that looks like this. If we do this with 600 bars, so notice this goes from 0 to 600. If I plot the frequency that I observe 0, and the frequency that I observe 1, and the frequency 2, the bars are so tightly packed together. They're so, densely packed. Really densely packed that you can't even tell them apart, right? If we were to stretch this graph out really, really far, then you could see where the individual bars are, right? But here you can't really tell. So, we've got a really densely packed set of bars. Now, a probability density function is like a histogram with an infinite number of bars, right? So, as we went from 5 to 10 to 100 to 600, as we were putting in more and more bars, we're getting a better idea about the true shape of whatever the population is, right? So if we continue to make more and more and more bars, we would get a really accurate representation of the true distribution. So I have actually plotted here how many observations you would expect from the distribution that I was sampling from. So I multiply the densities by 1,000,000, because probabilities, they don't go from 0 to 7,000. What do probabilities go between? 0 and 1, right? The probabilities go between 0 and 1. So I multiply the probabilities that I have for this function by 1,000,000, right? The probability of observing something like this is really, really tiny. I multiply that by 1,000,000 to get the number of observations that I would expect. Remember when we were talking about flipping coins? If I flipped a coin 1,000 times, what observation would I expect most? 500, right? what observations would I expect next most if it was a fair? 499 and 501, right? So these are basically telling us what we would expect to see. At least the red is. The black is just that histogram that I plotted before. The red is telling us how many items we would expect to see if we had the probabilities that I actually have and know and can compute in R for this particular function. So, this is awesome. Now we can talk about a whole bunch of different distributions. So let's talk about the normal distribution. So the normal distribution, people talk about this as like a bell-shaped curve, because it looks kind of like a bell. It's also known as a Gaussian distribution for those of you who are interested. I won't ask you that on the test, but it is. So this is a normal distribution. Now, let's see if we can figure out where the mean, the median, and the mode should be. Where should the mean be? The mean should be at 100? Does anyone disagree? How did you figure that out?
Multiply from 1 to 200.
You multiplied from...
No.
You summed? You did this sum in your head?
No, you can see that it's symmetrical.
Ha ha ha! She picked up on something really easy. It's symmetrical. Right? It's symmetrical. And if you have a symmetrical shape, if you think about the mean as being a balance point, if I were to, imagine we had a paper cutout or a wood cutout of this. If I wanted to hold it on my finger, where would I hold my finger? Would I hold it here? What would happen if I held it there? Boom, it'd fall over. What would happen if I held it there? Boom, it'd fall over the other way. If I held my finger right there, balance, right? So the mean is like the balance point. Let's see if that's right. Oh my goodness, it is. Yes, that's the mean. What's the median? 100. How do you know that? It's in the middle, right? The median is the middle point. It's the point that 50% of the observations are going to be that or above, and 50% are going to be that or below, right? What point is that? Well, for this distribution, which is symmetrical, it's also the same dang thing. How about the mode? 100. How do you know that? It is symmetrical, but that's not necessarily why you know that. Because if I made a distribution like this, I mean, imagine that that's symmetrical. What would the mode be? There would be two modes, right? So the mode isn't necessarily in the middle. The mean, what is it? Well, it's right in the middle. The median, what is that? It's the same thing. It's the middle point, right? But the mode is not necessarily the middle point, even for a symmetrical distribution. So how do we know that it's the mode? Yeah, it's the highest point. This is the highest point, right? So because that is the highest point, that's how we know that it's the mode. Yay. So this is the normal distribution. With the normal distribution, the mean equals the median, which equals the mode. For a normal distribution, they're all the same thing. Okay? Well, that's an easy one. Let's take a look at a non-normal distribution. Let's look at a distribution with small positive skew. Okay, here's a new term, skew. So skew indicates a non-symmetrical distribution. So this is not exactly symmetric. Positive indicates more unusual values are on the right. So it means that this side is a bit heavier than this side is. Now, it might be hard to tell that this has small positive skew if I show you an example and ask you, is it positively skewed, negatively skewed, or not skewed? I will make them skewed enough where you should be able to eyeball it and tell me immediately. This is maybe not quite that skewed. But okay, this is small positive skew, so what should we expect? Where's the mean going to be? If there's a little bit more mass, if there's a little bit more density on this side, where's the balance point? Is it in the middle? Is it a little more than that side? Or a little more on this side? It's going to be a little bit more on this side, right? How about the median? The median should be 100? I don't actually know if 100 is...
Yeah, it's all.
So that's the middle score. How about the mode?
The mode is the highest.
The mode, that's easy. That's right here. All right, so let's plot these. So the mean is just a little bit over on this end. The mode goes right through that top point that we had earlier. And the median is very, very close to the mean. Notice that with the small positive skew here, we have the mode, the median,